that work. And let's try to share here. Okay, just give me a second. Let's work. Come on. Get my desktop set up here. Let's see. Chat. Okay. All right, so we're going to cover 12.5 today. So we're going to talk about how to describe lines and planes in three-dimensional space. And we're going to start with lines because they're a little bit simpler to think about. Right, so imagine you have your coordinates in the background here, and you've got a line that's lives in three-dimensional space. You can use a vector to go from the origin to some point on the line, and another vector to go to another point on the line. So say that's point P0, and this is point P1. So P0 is the point with coordinates x0, y0, z0. P1 is the point with coordinates x1, y1, z1. And you could think about making a vector that goes, say, from P0 to P1. And let's just write that down. So this is a notation we use sometimes to represent the vector in terms of its starting point and ending point. So what would this vector look like, given what we have down on our notes so far? Okay.
Wouldn't it map? It would map directly over the line.
So it would be the vector right here. Okay, good. That goes from P0 to P1. What are the coordinates of that vector going to be? So if I want to write this out in terms of its coordinates, what are those going to be?
x1 minus x0.
Okay.
y1 minus y0, z1 minus z0.
Very good. Okay, and if that is not clear to you, think about the triangle law for our vector addition. Right, based on this picture, we need to go from the origin to P0, at which case we're at the coordinates x0, y0, z0, right? So we can think of x0, y0, z0 as the position vector for this point. That, remember, position vector is the vector that gets you from the origin to your point. And then if we add the vector that goes from P0 to P1, oops. We should wind up at the point P1 if we add these vectors. In fact, that does what we're looking for. Right, so this now is the position vector for the point P1. And remember that for our purposes, right, we're not going to distinguish between vectors that have different initial points, initial starting points. So there's lots of vectors parallel to this vector from P0 to P1. Really, the only thing we care about in terms of characterizing the line is the direction of that vector. Right? Any other vector that we could lie down on top of the line is going to be parallel to that first vector that we produced right here. And that, in fact, is how we're going to characterize our line geometrically. So the geometrical characterization of points on the line is that we're going to say R, this vector R, is the position vector for some arbitrary point on the line. And that's going to be some vector R sub 0. We could think of R sub 0 as this vector that gets us onto our point P0 on the line, plus some arbitrary multiple of a vector V that is parallel to the line, that gives us a direction to the line. Okay, so that is our vector equation for the line. Does everyone, why did you add the P0? So Katie, could you expand on your question?
In like the line second to the bottom, you had the vector from P0 to P1 down there. I understand that, but I don't, why did you add the P0 right there?
Why did I add those two vectors?
Yeah.
So we've got a picture here, right? We've got this vector that takes us from the origin to P0,
Mm-hmm.
and another vector that takes us from P0 to P1.
Mm-hmm.
The triangle law for addition says that if I add those two vectors, that should be equivalent to the vector that takes me from the origin to the point P1.
Oh, okay. Thank you.
Okay, that's the picture. If you go to this equation, that's telling you what's going on with those vectors in terms of the coordinates. X0, Y0, Z0, that's the vector that takes you from the origin to P0. This guy on the right-hand side, that's the vector that takes you from the origin to the point P1.
Okay.
So what did we add? We added the vector from P0 to P1. That's exactly this vector in the middle.
Okay. I understand now.
Very good. Are there any other questions before we move on?
Wait, is that t times the vector all in the equation at the bottom?
This is a V. Okay. R equals R0 plus TV.
Okay. Thank you.
You're welcome. So the names here of these vectors don't really matter. It's traditional to use a V for the direction vector of the line, right? This vector V here is telling us some vector parallel to the line. So the vector or the geometrical equation so try to do this in a non-cursive script. So hopefully this is easier to distinguish. So in terms of components, this vector R, right, has components X, Y, Z. This is an arbitrary point on the line. Or it's the position vector for an arbitrary point on the line. Okay. R0 is the position vector of one fixed, we could call this a base point on the line. And then TV here, T is a parameter, right? Could take any value from -infinity to infinity. And V is the direction vector for the line. Right, so this R0, think of it as X sub 0, Y sub 0, Z sub 0, just the coordinates of some point which we know is on the line. And then TV, think of T times ABC, just some vector. So if we break all of this down into the components, the X component is telling us X equals X0 plus TA, Y is Y0 plus TB, Z equals Z0 plus TC. And we want our T to go, whoops, from -infinity to infinity. Okay, what we just produced here by breaking the vector or the geometrical equation of the line into its components, this is called the parametric equations for the line. The set of equations is the parametric equation for the line. And notice the information in this representation, the vector or the geometrical equation for the line, and in this representation, the parametric equations for the line is exactly the same. We're just presenting it in a different way. If I know my vector equation, I just break it up into components to get the parametric equations. If I know the parametric equations, like question? Did somebody have a question? Okay, someone's mic is on. Do you have a question? All right, I guess not. Please type out your question or ask it. Don't be shy about asking questions. So if you've got the parametric equations, you can just put those together, right? Each one is going to give you information about one of the components in the vector equation for the line. So from the parametric equations, you can read off that X0, Y0, Z0 are the components of a known point on the line. And you can read off that A, B, C are the components of a direction vector for the line. And finally, before I change the page, does everyone have what they need here? Okay. Finally, we have the symmetric equations for the line. Okay, and you can get these by effectively looking at the parametric equations and solving for the parameter t in each of these equations. So let me just reproduce the parametric equations here. So if I solve for t in each of these, in the first equation, I get t equals x minus x0 over a. From the second equation, I solve for t, I get y minus y0 over b. And in the third equation, I get z minus z0 over c. Now, in this form, the symmetric equations look symmetric, actually. We sort of got the same type of fraction we've built out of x, y, and z. If any of these coefficients a, b, or c are 0, then the symmetric equations are not quite so symmetric anymore. So if a equals 0, for instance, right, obviously we can't divide by 0. So what do? We solve for t if possible. So we're going to be able to solve for t in the y and z equations. When a is 0, we just have x equals x0. And then the other symmetric equations are y minus y0 over b equals z minus z0 over c. Okay. So again, the symmetric equations are a way of representing the line. The information you need to represent the line is the same no matter what form you choose to present it in. If you're given the symmetric equations, from these equations, you can read off that the direction vector or a direction vector would have components a, b, c. A base point you know is guaranteed to be on the line. Its position vector would have coordinates x0, y0, z0. Right, so you need to be familiar with these three ways of representing a line, and you need to be able to go back and forth easily between any pair of these. Okay, so everyone okay so far? Okay, we've got a question. Would the values of these equations be a vector or a scalar? Well, the vector equation is written in terms of vectors, right? You've got the r sub 0, and the v. Both the symmetric equations and the parametric equations are written in terms of scalar quantities. They're really written in terms of the scalars that make up the components of the direction vector or position vectors of the points on the line. Okay, so I tried to be consistent about indicating vectors with an arrow on top. In this case, the way I wrote them, if there's no arrow on top or a bar underneath the symbol, then it should be a scalar symbol. I'm not sure if I'm answering your question, Rachel. Is this making sense? Okay. So that's the story for lines. Before we go on, I just want to point out, if you think about these parametric equations for the line, right? These give you what's called a parameterization. For the line. And that is not unique. Right? There's many ways to produce a parameterization for the line. So the base point on the line, it can be any point on the line. Right? It doesn't matter which point you pick for R0. You just need some point which you know is on the line. And in the same way, the direction vector can be replaced by any non-zero scalar multiple of V. It's important that you replace your direction vector by a non-zero scalar multiple. And let's just draw a picture to make sure we understand what's going on here. We've got our line. Okay, think of this in three-dimensional space. The idea with our vector representation is we get onto the line by this base point R0, and then we get to any other point by taking, let's say this is our V vector. We're going to have to take some multiple of V to get from our base point to another point on the line. The value of T, right, is going to depend on exactly what point we're talking about. But if T is 0, we're at our base point. If T is positive, and this is our V, as T ranges from all the numbers bigger than 0, we're going to trace out all the points on this side of the line. If T is negative, we're going to trace out the points on the other side of the line. Well, there's nothing special about this arbitrary point we chose to get onto the line. We could pick a different point on the line. So R sub 0, I don't know, let's call it S sub 0 instead, right? This is a different base point on the line. And if we pick a different direction vector, we want to get to different points on the line. Again, we can take arbitrary scalar multiples. If we use the symbol T to get to another point on the line, right, the T is not going to mean the same thing in these two representations, but we're really doing the same thing. And again, as T ranges through all the numbers bigger than 0, we're going to trace out the points on one side of our base point. As T ranges through all the numbers less than 0, we're going to trace out all the other points on our line. So this is important. It's important to recognize you have this non-uniqueness in a few different places, one of which we're going to mention in a couple of minutes. All right, so just keep that in mind. Before we move on, are there any questions on what we talked about on this page? Is everyone good? Okay. So come on, don't do that. In a number of applications, we're going to want to parameterize, a line segment. So if we get our line, let's say we've got a point R0, R1, right? These are the position vectors for these 2 points on the line. And let's say we want to parameterize this line segment. Well, we can do that essentially by thinking about parameterizing the line. Choose R0 as our base point. And we want a direction vector that will point from R0 to R1. Right, so here's our direction vector. This is our base point. Notice that when t is 0, we're exactly at the point R0. And when t is equal to 1, we have R0 plus R1 minus R0, or just R1. So this equation, but with our parameter t restricted to lie between 0 and 1, will let us get all the points on the line segment. Okay, so does that make sense? Okay, so please ask if you've got questions.
Why t is between 0 and 1?
Because I'm trying to parameterize the line segment, just
Oh, okay, okay.
this set of
Yeah.
points.
Okay, I see.
Okay.
Yeah.
So that's something that for a number of purposes you might want to do, just to think about one piece of the line rather than the whole line. All right, and again, this is not unique. Okay. It does have the feature that you can see sort of in a nice way how to build this parameterization, as long as you know the two endpoints of the line and exactly how you want the segment to be traced out. Okay, so again, for lots of applications, you might want to do to figure out how two lines are related, right? So two lines in three-dimensional space could be related in one of three ways. They could be parallel to each other. In which case they could either not intersect, in which case we say the lines are distinct, or they could be parallel, in fact, lie on top of each other, in which case we would say the lines are identical. And every point is in common between the two lines. They could intersect in one point, exactly one point, or if neither of the first two possibilities is satisfied, we say the lines are skew. Right. Non-intersecting, non-parallel. And it might take you a second to think about how two lines could possibly be skew if you're thinking in terms of two lines on the two-dimensional plane. This is not a possibility if your two lines are restricted to two-dimensional space. But here's an example of skew lines. Think of your three-dimensional coordinate system. And think of a line which lies along the y-axis, and another line which lies in the xz plane, parallel to the x-axis, but 1 unit above the x-axis. Right, so these two lines are certainly not parallel to each other, and they certainly don't intersect. Okay. Can we go back 1 second? So to this page, Ava? Did you have a question, or do you just need time? All right, so the last line is just saying that this parameterization we've written down here is, as always, not unique. Okay. You set, Ava? Okay, good. So these are the possibilities. There's 3 possible ways that lines could be related to each other: parallel, intersecting, or skew. And the problem of distinguishing between these is you could think of it as a geometrical problem, right? You could try to draw the lines in 3-dimensional space, or you could think of it as an algebraic problem. You can work in terms of the parameters, the parameterizations of the two lines, and do algebra with the coordinates. So does anyone need more time on this page? We good to go? Okay, so the strategy for dealing with problems like this is first check if the lines are parallel. So if you've got line 1 and line 2, lines are parallel if the vector v1 is parallel to vector v2. But how could you characterize whether two vectors are parallel to each other? How could you check if two vectors are parallel to one another? You could take the dot product, and what would you have to what would happen to the dot product if the vectors were parallel? Well, it wouldn't equal 0. So if the vectors are parallel to each other, they point in the same direction. So the angle between them could either be 0 or 180. If you take the dot product, that means that you're going to get a factor of either 1 or -1 from the cosine. So the dot product, if you take the absolute value of the dot product, would just be V1 at length of V1 times length of V2. So you could do that. That's not the easiest way to do it. The cross product would V0 if the vectors were parallel. But maybe an easier way is to just look at the two vectors. If you can build one as a scalar multiple of the other, so a non-zero scalar multiple of the other, the vectors are parallel. So for instance, if I have the vector 1, 2, 3, and the vector 2, 4, and I don't know the third component, how could I make these two vectors be parallel to each other? Well, it looks like the second vector is 2 times 1, 2, and then I need something. So 1 matches up, 2 matches up. I would need the 3 for these vectors to be the same. So 1, 2, 3 is parallel to 2, 4, 6 because 2, 4, 6 is the scalar multiple 2 times the first vector 1, 2, 3. Okay. So that's probably the easiest thing to check. And if the vectors are not parallel, well, if the vectors are parallel, then you can check whether they are distinct lines or identical lines. Just pick a point which you know is on one of the lines, say R0, and see if you could get any points on one line on the other line.
Professor, I have a question not really related to what we're doing now, but the dot product is equal to 0 when two vectors are orthogonal, right?
Yes, correct.
Thank you.
Right, so the vector v1 is parallel to v2. It's some scalar multiple of v2. If I can get to one point on line 1, if I can show that line 2 contains at least one point of line 1, then when they're parallel, the two lines have to be identical. So I'm going to check. Oh, fudge, that should be a 0, that should be a 1. Okay, so this is my right-hand side for line 2. So can I pick T to get to a point which I know is on line 1? Right, so what's that saying? The difference of the base points here, right? If I subtract those two vectors, I should get a vector which is parallel to one of my direction vectors. Okay, if that can be satisfied, then your lines are identical, otherwise they're distinct. So is that clear to everyone? Everything good?
Can you just explain that part one more time?
All right, so I've got two lines. I know the representation in terms of base points R0, R1, direction vectors V0, V1. Okay, so there's two possibilities. Either the lines are right on top of each other. Do red and black for my two lines. Or the lines, in fact, are separated. They either share every single point or they share no points. Is that much clear?
Yeah.
Okay, so if I've got two base points on the line, right? There's my black base point and my red base point. When the two lines are on top of each other, if I form the vector that gets me from one of those to the other, that takes me along the line, right? So
Yeah.
that vector would have to be some scalar multiple of one of the direction vectors that I have for the lines, right? It has to be parallel to the direction vector for the line.
Yeah, that makes sense. Thank you.
That's what we're saying here. So if here's my R1 and here's my R0, if I build the vector that takes me from one of these to the other, notice that's not parallel to the two lines, the direction vectors for the two lines, if the lines are displaced from one another, if they're distinct. Okay. So the next thing to check is if the lines are not parallel, do they intersect? Right, so we could have two lines that intersect in one and only one point. So here's line 1, here's line 2, and we could say that line 1, we have R equals R0 plus T V1. Line 2, we have R equals R1 plus, damn it, TV1. Right, R equals R0 plus TV0, or R equals R1 plus TV1. Now, if there is an intersection point, that means there's a point I could reach from each of the lines. So the strategy is going to be to write that point of intersection in terms of line 1 and in terms of line 2. But you have to be careful when you do this, right? Because for line 1, let's say here's your base point. You have to move a certain distance to get to the intersection. For line 2, maybe you've got this different base point and you have to move a certain distance to get to the point of intersection. So representing your coordinate is going to be done in terms of the parameters of your line, but the parameter means different things on the two lines. So I don't want to use the same symbol. Okay. So if R0 has coordinates x0, y0, z0, and let's say V0 has coordinates A1, B1, C1, and in the same way, let's say R1 has coordinates x1, y1, c1, and the direction vector v1 has coordinates a2. Sorry, keep messing my coordinates up here. So v0 has got coordinates a0, b0, c0. v1 has got coordinates a1, b1, c1. I can't put t in as my parameter because the t's are telling you what multiple of your direction vector on the line in question are you moving from the base point on the line in question. So I have to give these two parameters different symbols. But what that leads you to is a set of three equations now in the two unknowns. Okay, so if that set of equations has a solution, then your lines intersect. If there's a solution to the set of equations, that means you can actually find the coordinates of this point of intersection. If there's no solution to the set of three equations, then you can't find this point of intersection and your lines don't intersect, in which case they are skew lines. All right, so that system has a solution. The lines intersect. And you, once you know S and you know T, you have the coordinates of that point of intersection. If the system has no solution, that means the lines do not intersect. And remember, we got to this point already assuming that the lines were not parallel. So if they're not parallel and they don't intersect, then they are skew in this case. All right, so we're running out of time here. So I think this is where I'm going to have to stop, and maybe we'll come back to 12.5 next time and talk about equations for planes and hopefully do some examples. Your lab tomorrow is going to be basically covering 12.6. So beyond lines and planes, we're interested in certain types of surfaces that come up frequently. So you'll get some practice using Mathematica to deal with surfaces in your lab tomorrow. All right, so any last questions before I stop sharing here?
Can you please go back to the previous page? Thank you.
Do you have a question or you just want to copy?
I want to take note. Thank you.
Do we have a quiz this week?
I will post the quiz for Friday that you'll take on your own time, okay?
Okay, thank you.
Any other questions?
Do you know what sections the quiz is going to be on?
Let's say 12.2, 12.3, 12.4. So vectors, dot product, cross product.
Thank you.
When is the quiz again?
It will be posted in time for you to see it on Friday, and it will be sort of that it's not going to be at a specific time. You'll have a fixed amount of time to work on it within some window.
Do we need to lock down browser for this?
Yes. So is everyone familiar with using the lockdown browser? Okay, we can talk about it on Friday if you haven't used the lockdown browser before. Don't freak out about it. It's easy to access through Canvas. Okay.
Will it say on Canvas what sections the quiz is over?
Yeah, I'll include that in the directions for the quiz.
Okay, thank you. Have a good one.
Okay, thanks everyone. So I'm going to stop sharing now. And I can hang around for a little while if there are more questions. Otherwise, please come back, and I have office hours, of course, later today. All right, everyone's gone.